Slide 7, chapter 7.
Professor,
Yeah,
can I record this Zoom session?
sure.
I think I need your permission, like,
Okay. How do you do that? Can't remember.
let me,
Okay.
yeah,
You go to participant, and then who is that? Is it Sudeep?
Deep,
So you wanted to record it?
yeah.
1 moment. Let me go participant. Invite. No. That's not. Oh, then I have to more. Allow record local voice. I think I did it.
Thank you, Professor.
No problem. All right, so let me share this first. Before you go to performance, we will go back to the pipeline. And the yeah, this is simple MIPS pipeline. So they follow these pipe steps. You need to memorize these pipe steps. Instruction page, and then instruction decode, the register page, and then execute, memory access, write back. So this is the 5 steps takes the MIPS pipelining. Now, definition of pipelining, we need to, and sometimes they use this IF for instruction fetch, ID for instruction decode, and execute uses LU, memory, data memory uses, and write back is WP. This is short form. So now we learn the definition of pipeline. So I'm going to write you that definition. I have. Let's look at the here, write it down here. So it's in the book. If you don't have the book, no one any excuse. And write it here. Definition of pipeline is an implementation. And implementation technique in which multiple instructions instructions are overlapped in execution. Overlapped in execution. Much like an assembly line. Much like an assembly ASSE. Assembly line. So that's the definition of pipeline. An implementation technique in which multiple instructions are overlapped in execution, much like an assembly line. So when multiple instruction you send them to execute, but they overlap sometimes. So what happens, like one is waiting for data for the previous instruction, but previous instructions not complete. So you just hold up a little bit, kind of a bottleneck, they call it. So that's the hazard. They don't call it bottleneck, but they call it pipelining hazard. So this is the definition you need to memorize. You may have short questions in the final. And then the instruction page that we have these pipe steps I mentioned before. Paste instruction for memory, read registers, decode instruction, execute operation or calculate an address, access an operand in data memory, write the results into the register. Down to. So these steps. And maps instruction. One, paste an instruction from memory. Fetch instruction you from memory. And when they call it IF instruction page shortcut. Read registers while decoding the instruction. While the read registers while decoding the instructions. That's number 2. Read registers while decoding the instruction. The regular format of MIPS instruction allow reading and decoding to occur simultaneously. That's fine. 3, execute the operation or calculate an address. Execute the operation. Or calculate an address. Or access an operand in data memory. Reading there. Access an operand in data memory. And then 5, is write the results into a register, that WB, right back. Write the result into a register. So this is the 5 steps and MIPS instructions, execution process. So you have to understand this 5. And so the analogy we have with the wash, wash dry clothes and folding and put into the shelf. Just explain like how pipelining helps to use your resources efficiently. That's the main point from that. Now, the pipelining doesn't always happen smoothly. It has some issues, some problems, some hazard, they call it. So this hazard, the next instruction cannot execute. So the hazard definition of hazard is there are situations in pipelining when the next instruction cannot execute in the following clock cycle. These events are called hazards, and there are three different types. So first one is structural hazard. First one, write it down, take notes or read it, memorize it. First one, structural hazard. Structural hazard. What is it? When a planned instruction, cannot execute in the proper clock cycle. Proper clock cycle because the hazard does not support, because the hazard does not support the combination of instructions. Combination of instructions that are set to execute. I need to memorize this definition of structural hazard. When a planned instruction cannot execute in the proper clock cycle because the hazard does not support the combination of instructions that are set to execute. So this is the structural. So it's structural issues, like hardware issues, basically the hardware issues, because it's not set properly. The MIPS instruction set was designed to be pipelined, making it fairly easy for designer to avoid structural hazards. When designing a pipeline, suppose, however, that we had a single memory instead of two memories. If the pipeline had a fourth instruction, you would see that in the same clock cycle, in the first instruction is accessing data from memory, while the fourth instruction is fetching an instruction from that same memory. Without two memories, our pipeline could have structural hazard. So that's the structural hazard. And then we have data hazard. Number two is the data hazard. It's a hazard, not hazards. Data hazards occur, also called pipeline data hazard, the same thing. So this one, when a planned instruction cannot cannot execute in the proper clock cycle. Execute in the proper clock cycle because the because data that is needed because data that is needed to execute the instruction is not yet available. It's not there basically. It's not yet available. So that's the data hazard. When a planned instruction cannot execute in the proper clock cycle because data that is needed to execute the instruction is not yet available. It's not there. So it's looking for data, but it's not there. So that hazard is data hazard. For example, like if you want to do a multiplication, of course you need two operands. And one operand is there, another operand is not there, so you cannot do the multiplication. So you have to wait for that other operand comes in to the pipeline. Then number 3, add sub, that's an example you can see in the book. Forwarding, also called bypassing, a method of resolving a data hazard by retrieving the missing data element from internal buffers rather than waiting for it to arrive from programmer visible registers or memory. So there is another definition here for forwarding or bypassing. So if you have a data hazard, and then how do you forward your instruction or bypass it? A method of resolving data hazard by retrieving the missing data element from internal buffers rather than waiting for it to arrive from programmer visible registers or memory. So that's the bypassing and forwarding. Load use data hazard, pipeline install bubble, or some other definitions. The third one is the control hazard. So that's 3 things you need to remember. Control hazard. Also, it calls branch hazard. Control hazard also, they call it branch hazard. When the proper instruction, proper instruction cannot execute in the proper pipeline, in the proper pipeline clock cycle, because the instruction that was fetched CHED, fetched, that is the pull-up instruction Instruction. Float instruction addresses is not what the pipeline expected. Pipeline expected. Pipeline expected. So that's the definition of the control hazard. When the proper instruction cannot execute in the proper pipeline clock cycle because the instruction that was passed, that is, the pool of instruction addresses, is not what the pipeline expected. So you're passing a wrong one, incorrect one. This kind of control. So the control didn't work. So it's supposed to come one after another, sequentially, but somehow it didn't happen sequentially in proper clock cycle. So that's the control hazard. Performance stall or branch. So this control hazard also called branch hazard. Remember that, branch hazard. That will happen like if then else statement, the control hazard step. Reordering code to avoid pipeline installs. Okay, so this example there. And for the control hazard, yeah, for the if then else statement, when you jump from one to another instruction, that time those control hazard may occur. Pacing the instruction following the branch on the very next clock cycle. Nevertheless, the pipeline cannot possibly know what the next instruction should be, since it only just received the branch instruction from memory. So just as with the laundry, one possible solution is to install immediately after we pitch branch, waiting until the pipeline determines the outcome of the branch and knows what instruction address to pass from. So some examples there. And then let's go back to the slides. So this three definition and also the steps in instructions, processing, core pipe steps, and then definition and implement pipeline. So this 3-4 things you must memorize or understand clearly that you can write. Okay, so that's important. So this is the hazard we've gone through, data hazard control, structural, and examples on the slides as well, so you can try to understand those. Structural hazard. And then we have all this pipeline, different cycle. Then talk about performance. Measuring performance is not trivial. So sometimes measuring performance in the pipeline is not obvious, is a little complicated. Sometimes it could be obvious, sometimes it's not that. So some example there you can see the when downtown SF, I need to get to the airport. So I have two options. We have more, but there's two options. Take BERT, about $8 per person, takes about 30 minutes, small carbon footprint, so environmentally friendly. Take cab, about $30 per cab, takes 15 to 20 minutes, more if bad traffic, large carbon footprint. Now, which way you will go? So it depends. Any idea which way you want to go? Anybody has opinion? Are you there, student? You can see 31 login. Are you there? Nobody is talking. Rita. So which option you take? You take bird or you take cat? I can't hear you. Rita.
It's not working very well.
Oh, Jie Cheng, when? Your mic must be working. Jie Cheng. Jie Cheng, when? Are you there? No. Elisa, Chi, are you there, Elisa?
Oh, there. It works.
Jie Cheng, it works?
Yeah.
So which option you go for?
You said car or
Cab or bird?
BART?
So you take bird?
Yeah.
Why?
Because the school gives me like the ID card and I get it for free, I think.
What ID card?
The SFSU ID card, and then it allows us to travel on the Muni. Yeah, the Gator Pass, Muni and BART for free.
Oh, free?
Yeah.
Wow. I didn't know that. So here, three option is not here actually. So you have, let's share again. So you have two options. About $8 per person. Takes about 30 minutes and a small carbon footprint. That's the point they gave you. You take a cab, you have $30 per cab. Takes 15-20 minutes and large carbon footprint. So you would go by bird, let's say $8. So the question is not very clear. Like, if you have, it doesn't say like, we are in downtown, like how many people here? Like, it's not clear, isn't it? How many people? So we, maybe more than one. So depends, like if you, $8 per person, if you have 4 people, then it's $32. $2 more than a cab. And the time, 30 minutes, it's pretty much will be the same, but cab may go past a little bit. But very unlikely. From downtown to the airport, no. Cab will not be faster because of traffic. Maybe 15-20 minutes is correct. But then 30 minutes of bird, is it 30 minutes from downtown? Sure, maybe lots of stations there. Take, and then, I mean, it depends on your situation. Like if you are in rush, or if you are actually arriving to the BART station on time, like, okay, maybe a couple of minutes you wait. Sometimes you have to wait 15 minutes for airport train. So it's a lot of, you see that a lot of variables here to make a decision. So you can just straight away say, oh, I mean, you can if you are clear about your motivation, like what do you want to do? If you're looking at carbon footprint, then of course you will take BART. It doesn't matter what. If you're serious about that, then you take BART. If you're not serious about carbon footprint and you're in business trip and you're kind of rush, then you may try to take cab. If less traffic, you may go faster. But the difference is not huge here in terms of the speed, like time and the money. Because if you're poor people, then you can, $30 cab is good. You actually cost you less, $2 less than the than the BERT. But if you are two person, then the BERT will be much better in terms of the price. So it depends, like what's your focus is, like what are you looking at? Money, time, carbon footprint, then you make a decision. So you see that it's a simple thing, but if you want to calculate and show your reasoning in terms of math, numbers, then it's not easy. And how do you put a number on carbon footprint for one trip, 20 minutes trip? How do you calculate that? This is very, very difficult to calculate. So depending on the situation and your resources and your time, you make decisions. So when comparing performance of two computer systems, we need to know the operation environment and what are we measuring. Suppose we're interested in running an application to perform a task. Example, convert CD tracks to MP3. The application can convert multiple tracks at the same time. That's the given definition. Response time, how long it takes from the beginning to end of a task. That's the response time. Throughput, how many tasks completed per unit time. So that's the throughput. Relative performance and speed up. We focus on response time. Common situation. Two systems, X and Y, run the same application, which is faster. We measure the response time on the two systems. Suppose X has a shorter response time. The speed up, always greater than 1, is defined as S, larger execution time divided by smaller execution time. So the execution time on Y divided by execution time on X. We say X is S times faster than 1. Okay. Example, X takes 10 seconds, Y takes 12 seconds. So the 12 by 10, X is 1.2 times faster than 1. Will take less time. More terms. Elapsed time. So total time for executing tasks, including input, output, operating system time, idle time. CPU time, time is spent by the CPU only one task. Unix time command gives 3 times. Real, system, user. So you can check it when you run it. Estimating performance of a program. How do you do that? Suppose we're interested in the performance of an application. Run the app with performance monitoring tools. Can count. Instruction count, total number of instructions executed. Percentage of each type of instruction, for example. 20% loads, 10% stores, 55% arithmetic logic calculation, 15% branches and jumps. That it takes. We'll run the MP3 encoder on our base PC, given the instruction code is 10 to the power 9, the cycle code. 10 to the power 9, given estimates for each instruction type. Each load takes 1.5 cycles. Each store takes 1.2 cycles. Each ALU instruction takes 1 cycle. Each branch takes 2 cycles. And total execution time in cycles will be, so loads times 1.5 plus stores times 1.2 plus ALU times 1 plus branch times 2, whatever it comes there. Suppose your PC has 2 gigahertz clock and 1 gigahertz is what? 10 to the power 12 picoseconds minus 12 picoseconds. Production time on the PC will be whatever comes in the calculation. How to get better performance? Suppose we buy a better compiler for our base PC. We decompile the MP3 encoder using the new compiler. And then you get different numbers. Each load now takes 1.2 cycles, this is 1.5. branch jump now takes 1.5 cycles. And what is the new execution time? Time spent on loads, time spent on stores, ALU. Just add them up together and then you get the speed. Cycles per instructions, another calculation. CPI. Loads take 1.5, store takes 1.2. So the cycle per instruction measurement for each cycle type will be number of cycles divided by instruction cycle. So this calculation used for the calculate the performance of a program. So I'm not very keen on the performance type because it's kind of not the focus of this chapter. CPI example here, cycle per instruction. Execution time and what's the formula? Instruction cycle times average. The cycles per instruction times cycles. Performance depends on algorithm, programming language, compiler, instruction set, hardware implementation. So all these variables are responsible for the performance. What kind of algorithm you use? What kind of programming language you use? Compiler you use? Instruction set architecture you use? Power consumptions, another example, the CMOS integrated circuits are the basis for most CPU chips today for this technology. Power equal to capacity load times voltage square times clock rate. That's the power. Capacitive load times voltage square times clock rate. Capacitive load depends on the transistor technology and the transistor fan-out. Number of inputs and output is connected to. Only limited reductions for capacitive load and voltage are possible. Cannot keep increasing clock rate. How to increase performance of a system? Multi-core process. And introduce multi-core process. Uniprocessor performance trend. Have a picture here from the 1978 to 2006. See how they going up the curve. Constrained by power, instruction level, parallelism, memory, latency. So this is the summary. MIPS CPU implementation, basic concept of pipelines, performance estimation. So here in the chapter, the performance estimation is, hazard is more important, and what we mentioned in here, also definition is more important. So I think I have some example. Oh, let's see. Example of performance measurement. I have some there. I'll put it up for you. You can look it up on the island, section 13. Basically, this I share. So these documents have some mathematics here. You can go through it. A couple of them. Relative performance. If a computer A runs a program in 10 seconds, computer B runs a program in 15 seconds, how much faster is A than B? We have an example on that slide. You know that A is n times as fast as B. If performance A divided by performance B equal to execution time B divided by execution time A equal to n. So the performance ratio is 15 divided by 10, 1.5. So A is therefore 1.5 times as fast as B. And then another example here. Our program runs in 10 seconds on computer A, which has a 2 gigahertz clock. We're trying to help a computer designer build a computer B, which will run this program in 6 seconds. The designer has determined that a substantial increase in the clock rate is possible, but this increase will affect the rest of the CPU design, causing computer B to require 1.2 times as many clock cycles as computer A for this program. What clock rate should we tell the designer to target? So that's the question. You read quite a few times to get it. And then the solution is given there too. Let's first find the number of clock cycles required for the program on A. The CPU time A equal to CPU clock cycles A divided by clock rate A. So 10 seconds equal to CPU clock rates A divided by 2 times 10 to the power 9 cycles per second, seconds in seconds. So CPU cycles A equal to 10 seconds time 2 to the power 2 times 10 times 10 to the power 9 cycles per second. So total is 20 times 10 to the power 9 cycles. CPU time for B can be found using this equation. CPU time B equal to 1.2 times CPU clock rate A divided by clock rate B. So 6 seconds equal to 1.2, 20 times CPU clock rate A divided by clock rate B. So clock rate B equal to 1.2 times 20 times 10 to the power 9 cycles divided by 6 seconds. So you get 4 gigahertz. 4 divided by 10 to the power 9, basically. So 10 to the power minus 9 is gigahertz. 1 gigahertz is 4 gigahertz here. To run the program in 6 seconds, B must be twice the clock rate as A. So that's with 2 gigahertz, now you need 4 gigahertz. So go through these questions 2 times and try to understand this calculation. But I'm not going to test you on this performance calculation. We have more other calculation to do. Okay, so that's I think the chapter. And that's all we have in chapter 7. CPU cycle stuff. Yeah. So there's quite a few things here. So the first, we look at this design MIPS implementation. So anybody has a chance to look at the video that put it there. Simple MIPS implementation, performance, pipeline. That's the things you need to learn from this chapter. And you need to memorize the definition as well, data path and control. The data path is registers, memories, glue logic, and connections. Basic part of the system is the data path. Control, active part of the system, directs data path to perform necessary action. So that's the control. Goal, design a simple CPU to support a subset of MIPS instruction. And then MIPS subset is 3 kind of instruction there. Simple one, R format, load, store, and branch. Simple single life cycle implementation. Why is it simple? Because instruction completes in 1 cycle. Cycle must be long enough for slowest operation to complete. And there are advantage and disadvantage for this. Advantage is simple cycle design is relatively simple. Disadvantage, inefficient. First instructions have to idle to wait post-load instruction. Now you think about this. This is simple implementation. And if you look at the steps and the processing flow for this, like this diagram, logic gate we have. Yeah, it doesn't look very simple, but it's relatively simple if you compare to other instruction set. So here use the program counter and then adder and some multiplexers. There's a couple of adders, 1, 2, 3, 4 adders, and multiplexer, quite a few of them they use. So it's not that complicated if you use the Logicsim or some other program and try to design this. Should be okay. So this is the list of control signals for setting data path. List to write, LU source, LU operand, memory read, memory write, memory register. LU has to do depends on instruction. So LU has the own instruction code. For load word of 00, store word 00. Branch equal to 01, R type is 10. So they have different kind of instruction there. Get familiar with this, the R type, load or store is the I type, and the branch is the J type. So just look through this and try to understand as best as you can. And so this one cycle is 10 to the minus 9 seconds. 1 gigahertz is 10 to the 9 cycles per second. Since 1 nanosecond is 10 to the minus 9 seconds, picoseconds is 10 to the minus 12 seconds. Very tiny time. And then we have this basic concept of pipelining from this doing laundry in 4 steps analogy. And then about simple MIPS pipeline, 5 steps, just memorize it. Now, instruction pass, instruction decode, execute, memory access, write back. Just memorize these 5 steps now. I'm going to ask you, go around and ask you. I'll not go to the next chapter today. This is today's chapter. So read it and memorize it. And I'll ask you in a minute. I give you 5 minutes for memorizing 5 instruction here, 5 steps. Instruction paths, instruction decode or register paths. Execute, calculate memory address, memory access, read data from memory, write back, write results back to registers. Are you doing it? It's important to focus on the class. Then you don't have to study after that. So you just, before the exam, you just review it and you'll be fine. So no stress. If you learn it on the fly, instead of pushing back, learn later. Is anybody ready? All right. Nobody turn on their camera, maybe all dead. That's okay. So we're going to ask randomly. Nicholas Thomas, are you there?
Yeah, hi.
Okay, can you say the 5 steps?
You got instruction fetch, instruction decode, execute, memory access, and write back.
Good. Are you looking at and reading it, or?
Yeah, I wrote it down.
Good. Shirley Ben, are you there?
I'm here. I haven't memorized it yet.
What's that?
I haven't memorized it yet.
You have not?
No.
It's okay. Do it now. It's in these slides, so you can download it and do it. This is important to learn now rather than before the final exam. All right, so there's some. How about the pipeline definition? Let's look at the pipeline definition. An implementation technique in which multiple instructions are overlapped in execution, much like an assembly line. Basically, you have an implementation technique that has multiple instructions and they're overlapping in the time of execution. So which one go first, which one is waiting, and that kind of stuff, situation. They call it pipeline hazard. Pipelining, basically. An implementation technique in which multiple instructions are overlapped in execution. All right. So now, then we have 3 hazards. Structural hazards. Okay, memorize the structural hazard now. If you have not written down, it's here. Have the on note out. Structural hazard. When a planned instruction cannot execute in the proper clock cycle. Okay, so read all those 3, and then I'll ask anyone from these 3. So give you 5 more minutes. Structural hazard, data hazard, control hazard. And what is it? Structural hazard. When a planned instruction cannot execute in the proper clock cycle because the hazard does not support the combination of instructions that are set to execute. So that's the structure. So it does not support the combination of instructions that are set to execute. And then data hazard, a planned instruction cannot execute in the proper clock cycle because data that is needed to execute is not there yet. Control hazard, when the proper instruction cannot execute in the proper pipeline clock cycle, basically when the instruction cannot execute in the proper pipeline clock cycle because the instruction that was passed, that is the pull-up instructions, addresses is not that the pipeline execute. I expect. So the instruction that was passed is not what the pipeline expected, basically. So that's the control hazard. The proper instruction cannot execute in the proper pipeline clock cycle because the instruction that was passed is not what the pipeline expected. It's not the right one. The pull-up instruction addresses is not what the pipeline expected. So there's 3 hazards, very important for your final exam. So you need to understand them and you need to learn an example of that as well. Anybody ready? Without looking at the notes. Well, some people have very good memories. They can just read once and get it. That's the thing, like in school, it doesn't matter like how better you understood something. But for the test and exams, of course, you have to memorize it. So if you understand it and then memorize it, probably you can remember a long time. But if you don't understand it, still can memorize it. Maybe it's for short term. Depends how good memory you have. Regardless, we have to memorize a decent amount in every course we do. Isn't it? Anybody ready? Jimmy Cheng. Are you there, Jimmy? No. Stephen Pong. Stephen Pong, are you there? Wow, students left already, I think. Some of them take the attendance off. Luis Ramirez. Are you there, Luis? I can see your name on the screen. So you need to talk to me, don't just text messages on the chat. We're not here for chatting. You can talk. Robert Bush, are you there? Robert? Nobody talking to me. Young So, are you there, Young?
Yeah,
Good. How many hazard we have there? Pipeline hazard.
like 3.
Correct. Thank you. You still talk. At least you talk. All right. Philip Chen, are you there?
Yeah,
So, what is a structural hazard?
without looking at the definition.
Yeah, just make it up.
I'm not really sure.
When a planned instruction cannot execute in the proper clock cycle because the hazard does not support the combination of instructions that are set to execute. This basically actually is hardware issues. Hardware issues, like your hardware does not support like many instructions executed at the same time. That's like if you have multi-core, then you can process more. If you have only one core, then you cannot. So that's that kind of hazard they call it a structural. Basically, like hardware is not there to support your instructions.
Okay.
Got it? Thank you. Jair Estrada, are you there? Jair,
Yes.
can you tell me what the data hazard is?
Data hazard?
Yep.
It's when I think it's something's trying to access some data, but it's not completely there yet or completely available yet.
Yeah, that's correct. It's not ready yet.
Right.
It's waiting for data to process, but it's not ready yet. So when a planned instruction cannot execute in the proper clock cycle because data that is needed to execute the instruction is not yet available.
Got
So
it.
example will be like, let's say you're doing a calculation, let's say some kind of calculation, but you're waiting for let's say you're using the temporary register or temporary variable, for example, and then you have 3 steps to do your calculation. And so those first 2 steps has to be done first, and result you use for the final calculation. So if those are not done for some reason, then you cannot do your final calculation. So that's the data hazard. You're waiting for data to arrive before you finish your instruction. And then the control hazard is slightly different. It's basically the logical. When the proper instruction cannot execute in the proper pipeline clock cycle because the instruction that was passed, that is actually not what the pipeline expected. So you paste something, like you load something to the memory, but you're not waiting for that, you're waiting for something else. So it's basically the if then else statement when we control things and do something, that kind of situation. So that kind of hazard, they call it control hazard. All right. So please read through this definition because I may ask you even in the next class. And of course, we have another chapter to go through next class. And I have very small material for this next 4 chapters. So make sure that we get it, memorize it, understand it, and should be able to answer questions.
Professor,
Yep.
can you repeat the examples you gave?
Second,
Can you repeat the examples for the hazards you gave?
which hazard?
The structural hazard.
Structural hazard. Structural hazard happens when the instruction, the combination of instructions supposed to execute is not supported by the hazard, by the hardware, basically, by the structure of your system. Okay, so that's the main hazard. Structural hazard is basically a hardware issue. So if you're trying to do some calculation, you need, let's say, 2 things, like 2 hardware, but it's not there, it's only 1. So then your 1 instruction has to wait for the other one to finish and then you do. So if you try to do a parallel programming in a single core machine, then may have some kind of hazard like this. So if you look at the book, they give you some examples as well, so you can try to understand those because it's necessary actually. So the structural hazard is necessary. The book has figure 4.27. 4.27 is this. In the processor, the example, load word, stored. So load word example, you can look at that and then it will be clear to you. Do you have the book, PDF version of this book? I think you should. I think I should have it because I put it on the island. So look at those PDF from the PDF book examples, or we can talk about that more in next class as well. All right, I think we are tail end of the time. See you in the next class.